Ushimara from Midwestern State University, and we'll have about 10 minutes, and then 5 minutes for the next speaker, and also for any questions. Go ahead.
Okay, hello everyone, my name is Eugene Yoshimura from Midwestern State University, and I will be talking about complex geometric approach and technique for trigonometry. How many of you have seen a similar topic that I've taught before? I see several hands, thank you. And I brought a new problem, so this is something new for all of you. Okay? And here's the problem. Is tangent 1 degree rational? This is a problem given in the entrance exam of Kyoto University in 2006, and it's known to be one of the shortest problem in math. And I'm pretty sure all of you are all good in math, so you can all solve this, but I'm just going to show a new way, okay? So before going into the new way, I want to explain what's trigonometry, what's tangent, although you all know there's opposite side and adjacent side, so it's a ratio of opposite over adjacent, and in order for tangent theta to be rational, if you can find a right triangle with some integer opposite side and integer adjacent side, then you will find a rational tangent. So for example, if you have a 45-degree right triangle, there is a ratio of 1 over 1, so you will get a rational tangent theta, tangent 45 degrees. But in another example, there's 30 degrees, and you will find the opposite side 1 and adjacent side square root of 3. That's gonna be irrational. And it is irrational because it's irrational divided by irrational. I'm not going into the detail why this is irrational because it's out of the scope of this topic, but I'm pretty sure all of you know that this is irrational. So let's talk about the new method, which I was being inspired from a friend of me called Miyu, and she had always struggled with the conventional math education system. She had never understood it because she's the kind of a person who thinks why first instead of what's the answer. So what she did is she just developed a new mathematical structure system by her own and evolved. So it's named Galapagosmetic. It's a tongue twister. It's hard to pronounce. Anyway, so what she did is define two numbers, 0 as an origin and 1 as a basis. And all the operations, the fundamental operations, can be defined in a symmetric way, such that addition is fixed basis or fixed 1, and moving origin or moving 0. Multiplication is fixed origin, fixed 0, and moving basis, moving 1. What does it mean? It's hard to understand without visualizing, so let me explain it. We have a number line on the real numbers, and let's try to do the multiplication of 3 times 2. The first step is to identify a multiplicand and a multiplier. The order is not so important, so if you want to switch the order, then you want to say 3 is the multiplier, 2 is the multiplicand, that's totally fine. But what's important here is you need to identify which one is which because they have different functions. So let me define it this way. I want to say 3 is the multiplicand, 2 is the multiplier. Then, from the original number line, I'm going to make a copy of a new one. And since it is a multiplication, I need to have fixed 0. Then, I'm going to stretch the new number line so that the new number line's 1, a basis, is adjusted to the multiplicand 3. Then, when you look at the multiplier 2 in the new number line, you're going to see that it is pointed at 6 in the original number line. So the answer is 6. And this is applicable not only for the real numbers, but also for the complex numbers. So I have a coordinate system. I want to perform a multiplication of 2 plus I squared. Again, this is 2 plus I times 2 plus I. I'm going to identify one of them as a multiplicand, one of them as a multiplier. So first, here's my multiplicand, and I'm going to stretch a new coordinate system, 1, which is a basis. Then, I'm going to find the multiplier on the new coordinate, which is here. So when you look at the new coordinates, 2 plus I, on the original coordinates, it's pointing at 3 plus 4i. So that's the answer of the multiplication. Let me talk about a new function, argument. Some of you might know this argument in complex numbers. We are talking about the angle from the real axis. So, for example, if I say argument of 2 plus I will be talking about this angle. Can you all see here? Here's the angle. Or if I want to draw argument on a new coordinate system, just like a while ago, then argument of 2 plus I is this one. What's interesting is that the original coordinate and the new coordinate are proportional, so the angle will stay the same. So if I have argument of 2 plus I squared, what I will get is 2 phi. And it is very intuitive to understand that the square here and the coefficient 2 here are corresponding to each other. And one more. Let's say there's some random complex number, and I want to take a theta. If I want to know a trigonometry, then I need to draw a right triangle like this. And tangent of theta is b over a, because b is the opposite side and a is the adjacent side. So we all have the necessary tools. So argument of z raised to n is equal to n times argument of z for some complex number. And argument of a plus bi is theta, saying that tangent of theta is b over a. That's all we need to know. And we are ready to prove the original problem. So let's go back. Main problem. Who thinks that tangent 1 degree is rational? No one. Who thinks it's irrational? I see a lot of hands, so let's go with irrational. I want to use proof by contradiction, so I'll start with assuming that tangent 1 degree is rational. Then, there exists some integer a and b such that tangent 1 degree is b over a, because it's rational. So it means there exists some complex number a plus bi that the argument will become 1 degree. And if I raise it to 30, then I should get 30 degrees. When I expand a plus bi raised to 30, that's binomial expansion. So I will get another complex number c plus di. And both c and d are integers. So tangent 30 degrees must be rational. But that's not true. So it's a contradiction. So therefore, tangent 1 degree is irrational. Clean and neat, right? I just finished proving in just one slide. Any questions? Yes?
So in that case, would any degree, would any degree that's a factor of 30 be irrational because you could still use similar exponential logic?
Yeah, you can use exponential logic. It's similar to like double angle, triple angle that you studied in trigonometry. I'm just showing in a new way.
I was just saying like 2 degrees or 3 degrees would also be irrational, would also result in an irrational tangent because you could still go to the 15th power, to the 10th power.
I see what you mean. So the multiple of irrational angle is always irrational. But no, not necessarily. multiple of irrational number can sometimes be rational. Like 1 degree raised to 45, that's going to be 45 degrees, that's going to be rational because irrational times irrational can sometimes be rational, right?
Well, 2 degrees would be irrational because if you raise 2 degrees to the 15th power, that would give you 30. So it would have to be. So by the same logic we use for 1 degree, it would also be irrational.
Oh,
That's
so
what I was
you're
asking.
talking about the multiples. Yes.
That's
Yes.
what I was asking.
That's right. Anything else?
Any other questions for the speaker? Yes, thank you for the speaker.